And here we go again. So now we've talked about interaction with charged particles, alphas and betas, and we talked about gamma rays. In several courses, there's where things end. That's not the case here. That's not the case because especially we here work at a nuclear reactor. And as I've hinted before, the nuclear reactor is essentially a very good source for neutrons. So we have quite a lot of neutrons here, right? During my physics course, I don't think I have ever really been introduced to the interaction of neutrons with matter. It's not really important for them. But for us who work in a nuclear reactor, it is really, really important, and sometimes it's the most important one. So let's think a bit, okay? Neutrons do not have charge, so they will not interact with the charge of the electrons. But they do not interact with electric fields either. If they do not interact with electric fields, they will not interact with the electric fields generated by electrons or by the nucleus, meaning that they will exclusively interact with the nucleus itself. As we hinted on the first class of interaction, interacting with the nucleus is much, much less likely than with electrons, right? This means that this neutron radiation is highly penetrating. In most materials, it goes a long way without being really disturbed. And another thing, we're talking about interacting with nuclei. And it's not only that. We're talking about there's scattering, that happens especially with hydrogen, but there's also nuclear reactions. And when we're studying nuclear reactions, I told you that neutrons, as they don't have charge, they can produce nuclear reactions even with very, very low energy. This means when we talk nuclear reactions, we have to think about making things radioactive. Sometimes you don't. You just take one stable nuclide and go to another stable nuclide. But many times it's not the case, and you get a stable nuclide and you transform it into a radioactive nuclide. So when we think about neutrons, I said to you that when we think about heavy charged particles and light charged particles, and even gamma rays, provided the energy is not that huge, you do not have to be afraid of leaving your sample radioactive, because nuclear reactions will not happen and you will not change your sample. You may destroy the electronics part, you may destroy chemical bindings, you may change completely the chemical composition, but you will still have the same nuclei there. Now, with neutrons, this is not true. You do not have the same nuclei, so when we think irradiating with neutrons, we must be very, very careful, because we're talking about making things radioactive. Okay? This has to be clear the whole time. So, for neutrons, there's the interactions of neutrons. They can be divided among several small things that happen, but essentially they are easier to understand if we divide the neutrons by energy. So the predominant energy in all ranges is scattering, and hydrogen is especially good at scattering neutrons. So if you think something that's scattering a lot and not doing much of anything else, it's almost the definition of an ideal gas you had in thermodynamics back there in school or somewhere. So what happens in an ideal gas? Remembering there are thermodynamics lessons. If you have a particle with very high energy entering a scattering media, or if you have a high temperature gas and a low temperature gas and you open your bottles, what happens? They start to collide or scatter with each other. Scattering, just another name for collisions, right? They start to scatter with each other, and the energy will be in the end divided by all of them. And if you remember, they will be, in the end, they will be left following Maxwell-Boltzmann distribution centered around 3/2 of Boltzmann constants times the temperature, right? So they enter what we call thermal equilibrium with matter, right? That's what happens if you have a hot gas and you put it inside a larger bottle, right? This is the same for neutrons. So neutrons, yes, they will enter a thermal equilibrium with matter just as if they were gases. This is very important. So you have very energetic neutrons that are produced in nuclear reactions in our reactor. And these neutrons, they will come into the medium and they will start to find nuclei to scatter, mainly hydrogen, thus the water in the reactor, right? So, and they start to lose their energy until they enter thermal equilibrium with the medium. And then, yes, they will follow a Maxwell-Boltzmann distribution centered in 3/2 of Boltzmann constant times the temperature of the medium, in this case the water in the reactor, right? And that's why we call them thermal neutrons. In fact, for 30 degrees centigrade, this energy, average energy of the neutrons will be approximately 25 milli-electron volts. Yes, that's right, 0.025 electron volts, right? Very, very low energy. But remember that neutrons can do reactions even at those low energies, mainly N gamma reactions. So those neutrons, we call them thermal neutrons, and they interact with the medium mainly by N gamma reactions. There's very few exceptions to these cases in which we may have N alpha reactions. And remember the 1/v law I showed you for reactions. Yes, this is essentially true. The cross-section is essentially proportional to 1/v. Just, again, this is a general rule of thumb, but there are exceptions, right? Then, if we increase the energy, we start to look at the neutrons that are in the way of losing their energy, but they're not still in thermal equilibrium. So they are above this 1 electron volt threshold. And this threshold, each book you see will give you a slightly different value. 1 electron volt is just a general number. You may find other numbers for this, all close to this. And then you have the epithermal neutrons. Epithermal meaning beyond thermal. So they are the ones that haven't yet got thermalized properly. They are in the process of losing their energy, but they are not there yet. So they have an average energy, and still the main interaction is via N gamma reactions. But now remember in the reactions class those resonances in the cross section I showed you, that all of a sudden the cross section started to increase a lot and decrease a lot very quickly. Yes, that's the epithermal region, right? So still N gamma, but a lot of resonances will start to interact more directly with the internal structure of the target nucleus. And then after some kind of energy, we call them fast neutrons. And now not N gamma reactions cease to be really relevant, and we start to have a lot of other reactions as the most important ones, right? So here just an example. This is a cross-section plot for platinum 195 N gamma. You see here the thermal region, very well behaved, 1/v, as we told before. If you don't just to remind you, 1 over v, meaning that the cross section will decrease with the increase of the velocity, right? Then all of a sudden you start to interact straight with the internal structure of the platinum 195 nucleus, and you start to have all these resonances. This is the epithermal region, and all of a sudden when you go beyond a certain energy, you see that the N gamma reaction cross section start to drop really steeply, and now other reactions will take place, right? So these are the fast neutrons, these are the epithermal neutrons, and these are the thermal neutrons. The main mechanisms of interaction of neutrons with matter are, as I told you, elastic scattering. Remember from reactions, elastic scattering, Q equals 0, meaning the energy is split but not transformed into gamma rays. And happens with neutrons in any energy range, and elastic scattering is much more well behaved. No, not the word I wanted. It's much more efficient if you use protons, because the proton has essentially the same mass of the neutron, meaning that in each collision they will lose in average half of its energy. If it collides with a much heavier nucleus, it will lose only a small part of its energy. It's just classical mechanics in this case, right? So happens with neutrons in any energy range, from the thermal neutrons to the very fast neutrons. So what happens most is elastic scattering, as I told you. Then you have inelastic scattering. In this case, the nucleus is left in an this is unexcited state. It's left in an excited state, right? So now there will be gamma rays emitted, and this happens at higher energies because you must deposit in the nucleus energy enough for the gamma ray that will be emitted, right? So usually a few mega electron volts for that, or several kilo electron volts at least. And N gamma, or radioactive capture, or absorption sometimes called. This is the most likely reaction with thermal neutrons. Remember, reaction we're leaving scattering aside, because scattering is just happens to all energies. So the most likely reaction that will kill thermal neutrons is radioactive capture, right? It can also happen with epithermal neutrons with all those resonances I showed you, but they essentially do not occur with fast ones. There's also charged particle emission, right? Like NP or N alpha, right? Usually happens with fast neutrons. There are notable exceptions, okay? For instance, these 2 N alpha reactions happen with thermal neutrons perfectly. Boron 10 N alpha to 7 lithium, or 6 lithium N alpha through hydrogen 3 to tritium hydrogen 3. Okay, but these are the exceptions. The general rule is you need faster neutrons for that. You have fission, of course. We've talked about fission, right? It happens with thermal neutrons in uranium-235, for instance, or with fast neutrons in uranium-238 or thorium-232. And when the neutron energy starts to get too large, I mean 100 mega electron volts or more, you may start to have what's called nuclear fragmentation, or other reactions like particle showers, what happens with the cosmic rays. And well, just forget that there's others also. Okay, but this is essentially what happens. Very high energy nuclear reactions, usually, remember from nuclear reactions, produce a lot of strange things. And when we're talking 100 MeV, you usually just obliterate matter, and you just obliterate everything, and whatever goes. Okay? So, now, when we were talking, once again, thinking we have to stop alpha particles, just anything is good. If you want to stop beta particles, also any matter, just if you want to avoid too much Bremsstrahlung, you should get lower Z material, so wood or something, plastic. And I told you that if you want to stop gamma rays, we need lead. We need high Z. Could be lead, could be bismuth, could be, sometimes people use tungsten, uranium, everything very heavy. When we talk in neutrons, we must remember one thing clearly now. We're talking about nuclear reactions. Nuclear reactions means one isotope is completely different from the other, right? We're not talking about specific elements, but now with specific isotopes. And more than that, we're talking of some very specific cases. So, for instance, lead is very bad at stopping neutrons. Neutrons just go through lead quite easily. Hydrogen is good for scattering. So, if you want, and cross sections are generally much larger for lower energy neutrons. So essentially, when you want to shield neutrons, we think hydrogen, not to absorb the neutrons, but to take the energy out from the neutrons so that they lose energy and they can interact more strongly with other materials. And then you have, for instance, gadolinium. Cross section of 50,000 barns, a whole lot. Of course, this is different among all isotopes of gadolinium. Gadolinium 157 is the most effective one, but in general, absorption is good for gadolinium in general. Boron, okay, there's this N-alpha reaction here, but it only happens with boron 10, 3,000 barns. Boron 11 is essentially transparent to neutrons. Okay, luckily enough, natural boron has a lot of boron 10, so it's cheaper to just use boron in general, and it's okay. Indium, absorption can be 200 barn also, but it's for a specific isotope. I don't really remember which. Cadmium has a very large cross section for absorption. And there's an interesting thing, cadmium has a very large cross section with quite a steep fall after 1 electron volt or something. That's why it's so usually used as a thermal neutron filter. You put cadmium, the epithermal and fast neutrons go through, but the thermal neutrons stop. Right? I don't remember which isotope, but cadmium, even in its natural form, is very good. Uranium 235, you have fission, it's 500 barns, it's large, right? So these are materials that interact strongly with neutrons. There's some others I could say. It's silver in general. Of course, in all of those, there's a specific nuclide which is the one that really interacts with the neutrons. The other ones are they just don't really matter. So if an element's good, means that isotope is dominant or something. So we have silver is very good, gold is very good at stopping neutrons, cadmium, indium, essentially that's the materials we use, right? So when we use here, for instance, the most common shielding we have for neutrons is some kind of hydrogenated material. Could be paraffin, could be polyethylene, could be high density polyethylene. We use it a lot. Mixed with boron, because boron is cheap right? It has a very large cross section, and it's easy to dissolve into hydrogenated material. So we have a lot of borated paraffin, borated polyethylene, and so on. Right? This is very good to stop neutrons because the hydrogen gets the energy of the neutrons and drop them back to the thermal region, and then boron takes place and just absorbs it, releasing an alpha particle which will stop inside the material itself, right? For the reactor, for instance, we have rods with indium, cadmium, and silver, which are used inside the reactor to absorb part of those neutrons. The fact that the cross sections are not so big is good, and the fact that they're all metals, so they can be easily usinated, also important, right? So that's essentially what we talk about. We're talking about shielding from neutrons. We're talking about hydrogen plus something that absorbs them. Could be cadmium, could be boron. These are the two most common ones. Okay? So that's it for today. Bye bye.